the part of the moon we never see from Earth, perpetually turned away and cloaked in darkness, has been a source of profound mystery for most of human history. For millennia, we had no direct knowledge of what lay on this hidden hemisphere. There were no landings, no close-up images, only the vast and silent canvas of the unknown. That all changed with the dawn of the space age. NASA, driven by an insatiable curiosity and the geopolitical imperatives of the Cold War, began to send missions, orbiters, and a suite of high-technology instruments to explore this enigmatic territory. What these robotic emissaries found was a world that was both alien and familiar, a landscape of stark and beautiful desolation. They discovered massive craters, the scars of ancient and violent impacts that shaped the early solar system. They detected strange and unexpected mineral compositions that did not seem to match anything in the moon's more familiar near-side geology. They picked up faint, ghostly magnetic signals, the fossilized remnants of a long-dead global magnetic field, a field that was unexpectedly strong and whose origins remain a source of intense scientific debate. And in the deep, frigid, and permanent shadows of the polar craters, they found the most precious and unexpected treasure of all definitive signs of frozen water. The far side is a place that, on the surface, looks dead and inert, a silent and unchanging world. But something about it, the sum of all these strange and disparate clues, does not quite add up. So, what is really out there on the far side of the moon, and why, after more than half a century of exploration, does it continue to hold such a powerful and enduring fascination for NASA and for the entire scientific community? The moon, our closest and most constant celestial companion, presents a single, familiar face to the Earth. For as long as humanity has gazed up at the night sky, we have seen the same unchanging patterns of dark, volcanic plains and bright, cratered highlands. This remarkable constancy is not a trick of light or distance. It is a fundamental and beautiful consequence of celestial mechanics, a phenomenon known as tidal locking. Understanding this gravitational dance is the key to grasping why one entire hemisphere of the moon remained utterly hidden from human eyes for countless millennia. A vast and mysterious territory shrouded in an enduring enigma that only the advent of modern spaceflight could finally unravel. Tidal locking is the end result of a long and patient gravitational conversation between a large primary body, in this case the Earth, and a smaller orbiting body, the Moon, over an immense and almost unimaginable span of cosmic time. The Earth's powerful gravitational pull has sculpted and shaped the Moon's rotation. The Moon is not a perfect, uniform sphere. It has slight, almost imperceptible bulges, both on the side that faces the Earth and on the opposite, far side. These bulges are a direct consequence of the Earth's gravity, which pulls more strongly on the near side of the Moon than on its center, and more strongly on its center than on its far side. This differential gravitational pull stretches the Moon slightly, like a piece of cosmic taffy, along the line connecting the two celestial bodies. In the early, chaotic history of the solar system, the Moon likely spun on its axis much faster than it does today. As it orbited the Earth, these tidal bulges would have been constantly slightly out of alignment with the direct Earth-Moon line. The Earth's immense gravity would have relentlessly tugged on these misaligned bulges, trying to pull them back into alignment. This constant, gentle tug created a torque, a rotational force on the Moon, which acted as a powerful and inescapable brake over hundreds of millions, and perhaps even billions, of years. This braking effect continued. The Moon's rotational energy was slowly dissipated, converted into a minuscule amount of heat through the internal friction of its own churning, rocky interior. This process was a one-way street, a relentless and irreversible journey towards a state of minimum energy, a state of perfect gravitational equilibrium. This equilibrium state is achieved when the Moon's period of rotation on its own axis precisely matches its period of revolution around the Earth. In simpler terms, the Moon now takes the exact same amount of time, about 27.3 Earth days, to spin around once as it does to complete one full orbit around our planet. This synchronized celestial waltz means that the same hemisphere of the Moon is perpetually and gracefully oriented towards the Earth. From our vantage point, it can appear as though the Moon is not rotating at all, but it is. Its spin is just perfectly and beautifully matched to its orbital speed. This is a common fate for large moons orbiting close to massive planets throughout our solar system and beyond. It is the natural, and often inevitable, outcome of a long and patient gravitational embrace. While it is true that the same side of the Moon generally faces the Earth, a series of subtle and beautiful wobbles, known as librations, allow us to peek, just slightly, around its edges over the course of a lunar month. These librations are caused by the fact that the Moon's orbit is not a perfect circle, but a slight ellipse, and its axis of rotation is slightly tilted. This means that, over time, a keen-eyed observer on Earth can actually see about 59% of the Moon's surface. But that still leaves a vast and tantalizing 41% of our nearest celestial neighbor, a territory larger than the continent of Africa, that is, forever and completely hidden from our direct line of sight. It is this large, truly hidden portion of the Moon that constituted one of the great and most enduring mysteries of pre-space age astronomy. For thousands of years, the far side was a blank canvas, a realm of pure, scientific, and imaginative conjecture. No telescope, no matter how powerful, could bend light around the limb of the Moon to reveal its unseen hemisphere. From the first, rudimentary spyglasses of Galileo Galilei in the 17th century, which revealed the Moon to be a world of mountains and craters, to the massive, ground-based observatories of the 20th century. Every instrument was fundamentally limited by the Moon's tidally locked orientation. This lack of direct observation meant that our maps of the Moon were, by their very nature, incomplete. They represented only the visible half of a world, leaving the other side to the realm of artists' imaginings and educated, but ultimately unprovable, scientific guesses. The true and only. Reason for this prolonged mystery was the absence of a single, crucial technological leap space travel. Until the mid-20th century, the concept of sending a robotic probe, let alone a human being, beyond the Earth's atmosphere was confined to the pages of science fiction. The engineering challenges were immense, the stuff of dreams. But the dawn of the space age, sparked by the launch of Sputnik, won by the Soviet Union in 1957, fundamentally and irrevocably altered this reality. Suddenly, what was once pure fantasy became a tangible and fiercely contested national goal. But even with the advent of powerful rockets, directly observing the far side posed a unique and immediate new problem: communication. A spacecraft on the far side of the Moon would be completely and totally blocked by the 2,159 mile of wide body of the Moon itself from sending its radio signals directly back to Earth. It would be in a communication blind spot, a cosmic radio shadow. Any data it collected, any images it captured, would be trapped on board, lost to us forever, unless a clever solution could be found. This challenge necessitated the development of advanced, and at the time, highly speculative, relay technologies, such as orbiting satellites that could receive a signal from a far-side probe and then retransmit it back to Earth. Without such a relay, any long-duration mission to the far side would be an exercise in futility, a journey into a silent and dataless unknown. The first, historic and successful venture to pierce this veil of mystery was undertaken by the Soviet Union. In October of 1959, their Luna 3 probe, a small and by modern standards incredibly primitive spacecraft, swung around the moon, becoming the first human-made object to ever capture an image of this enigmatic and long-hidden territory. The images were crude, blurry, and distorted, the product of a primitive, on-board, film processing and scanning system, and a tenuous, long-distance radio link. But they were revolutionary. They were the first flickering and ghost-like glimpses of a new world, and they revealed a landscape that was immediately and strikingly different from the familiar face of the near side. The images showed a surface that was much more heavily and uniformly cratered, and was notably and almost completely lacking in the large, dark, volcanic plains, the Maria, that so prominently defined the visible lunar landscape. This initial, stunning revelation confirmed that the far side was not simply a mirror image of the near side. It possessed its own distinct geological character, a character that hinted at a different and perhaps more ancient evolutionary history. The excitement generated by these first distant photographs was immense, and it set the stage for a new era of lunar exploration. An era in which the once hidden far side of the moon would slowly and beautifully yield its long-held secrets to the relentless and insatiable curiosity of a new and spacefaring human species. The blurry images from Luna 3 were a tantalizing first step, but they were far from providing a comprehensive understanding. NASA, then a relatively young but ambitious space agency, quickly began its own parallel program of lunar exploration, a program that would culminate in the historic human landings of the Apollo missions. While these early NASA missions, for practical reasons of landing site selection and communication, were primarily focused on the near side, the scientific imperative to explore and to understand the entire moon, including its hidden, far side, remained a powerful and enduring driving force. The journey to unveil the hidden moon was long and arduous, a journey that required decades of meticulous scientific planning, of breathtaking technological innovation, and of a fierce international competition that would ultimately push humanity beyond its terrestrial cradle and out into the vast and beautiful mystery of the cosmos. The human fascination with the moon, and with the heavens in general, is a story that is as old as our species itself. Before the advent of the scientific method, before the invention of the telescope, and long before the very concept of space travel had entered our collective imagination, the moon was a mystical and powerful object, a luminous silver orb in the night sky that inspired awe, wonder, and countless myths. Ancient civilizations across the globe wove elaborate and often beautiful tales around this celestial body, associating it with deities, with fertility, with the inexorable passage of time, and with the deep and often frightening mysteries of the night. It was seen as a silver chariot, driven by a goddess across the celestial vault, as a watchful and sometimes judgmental eye gazing down upon the affairs of mortals, or as a powerful and often capricious entity that influenced the tides, the harvests, and the very rhythms of life and death. These early pre-scientific inquiries were not about physical travel, but about finding meaning, about understanding the moon's nature and its spiritual significance in a universe that was, for the most part, a deep and terrifying unknown. But even in this age of myth, the seeds of a more scientific understanding were being sown. The ancient Greek philosopher Anaxagoras, in the 5th century before the Common Era, made the bold, and for his time, heretical suggestion that the moon was not a divine light source, but a rocky, Earth-like body, that its light was not its own, but was merely the reflected light of the sun. This was a radical and dangerous idea, one that challenged the prevailing mystical beliefs of his time, and one that laid a foundational, if rudimentary, stone for the great edifice of scientific inquiry that was to come. Aristotle, another towering figure of ancient Greek thought, built upon these early observational insights, integrating them into his comprehensive, and for centuries, dominant, geocentric model of the universe, a model in which the Earth was the fixed and special center of all creation, and all the celestial bodies, including the moon, moved in perfect, crystalline circles around it. While his model was ultimately, and spectacularly, wrong, his systematic and deeply empirical approach to observing and theorizing about the cosmos would influence Western thought for over 1,000 years. The idea of the moon as a world, a place of substance, a destination, began to take a tenuous but persistent root in these early philosophical inquiries. The dream of flight, of transcending our earthly bonds, also permeates the myths and legends of the ancient world. The story of Icarus, who fashioned wings of feathers and wax and attempted to fly to the sun, only to have his wings melt and to plunge to his death in the sea, is a powerful and enduring allegory for humanity's deep, and often tragic, aspiration to conquer the skies. While these were not direct dreams of space travel, they represented a fundamental and deeply human yearning to escape the confines of the Earth's surface, a necessary psychological precursor to the grander, and at the time, unimaginable, ambition of reaching other celestial bodies. For many centuries, the lack of a fundamental, scientific understanding of the basic principles of physics, of gravity, of the nature of the atmosphere, and the vacuum of space meant that the concept of traveling to the moon remained firmly and safely in the realm of fantasy and allegory. It was a subject for poets and storytellers, not for engineers and scientists. The 17th century, however, marked a pivotal and revolutionary shift. The invention of the telescope and its subsequent brilliant application to the heavens by Galileo Galilei fundamentally and irrevocably transformed our understanding of the universe. Galileo's telescopic observations in the early 1600s revealed that the moon was not the perfect, smooth, and ethereal sphere of Aristotelian philosophy, but a rugged and deeply familiar world, a world with mountains, with valleys, with vast dark plains, and with countless craters, a landscape that was, in many ways, strikingly similar to the landscapes of our own Earth. He even, with a beautiful and simple piece of geometric reasoning, estimated the heights of the lunar mountains by carefully observing the lengths of the shadows they cast. This new empirical evidence, derived from direct and repeatable observation, solidified the idea of the moon as a physical body, a world in its own right, a place that one could, in principle, visit. This new scientific understanding spurred a new wave of imaginative leaps, a shift from the realm of pure myth to a more grounded, albeit still fictional, exploration of the practicalities of lunar travel. In the mid-1600s, the French writer Cyrano de Bergerac, in his comical history of the states and empires of the moon, imagined a series of fantastical, but for the first time, vaguely mechanical, methods of reaching the moon, including using dew-filled bottles that would be drawn upwards by the morning sun, or a machine powered by a series of firecrackers, a primitive, but recognizable, rocket. Around the same time, the English bishop Francis Godwin, in his The Man in the Moon, described a protagonist who travels to the moon in a chariot pulled by a team of trained and exceptionally strong geese. These narratives, while charmingly unscientific, were significant. They represented a new and deeply modern human desire to imagine the mechanics of such a journey, to grapple, however imaginatively, with the practical challenges of space travel. The 19th century saw a flourishing of this new genre of speculative fiction, a genre that increasingly and skillfully intertwined the latest scientific concepts with bold, imaginative storytelling. The French novelist Jules Verne became a titan of this new form. His 1865 novel, From the Earth to the Moon, is perhaps the most famous and influential work of early space travel fiction. Verne's concept for lunar travel was a giant, spacefaring cannon, the Columbiad, which would fire a projectile containing 3 intrepid passengers directly towards the moon, while a cannon launch would, in reality, be instantly lethal to any human occupants due to the immense and crushing G-forces. Verne's attention to scientific detail was, for his time, remarkable. He consulted with scientists and engineers, and he meticulously, and for the most part, correctly, calculated the required muzzle velocity to escape the Earth's gravity, the trajectory of the projectile, and even the financial cost of such an immense undertaking. He described, with a surprising degree of accuracy, the experience of weightlessness in space and the challenges of life support in a sealed and very small capsule. His work captivated the public imagination and, in a subtle but powerful way, introduced the fundamental principles of ballistics, of orbital mechanics, and of the very possibility of space travel to a vast and hungry popular audience. Another great 19th century author, H.G. Wells, in his 1901 novel, The First Men in the Moon, conceived of a more scientifically imaginative and, in some ways, more prophetic method of propulsion, a substance he called cavorite, which had the magical property of nullifying gravity. While entirely fictional, this concept allowed Wells to explore the idea of a controlled and returnable flight to the moon, and to create a vivid and often terrifying portrayal of a complex and ancient alien civilization of insect-like selenites who lived in vast underground caverns. These literary works were crucial. They were a necessary imaginative bridge between the pure fantasy of the ancient myths and the burgeoning, hard-nosed, and practical fields of physics and engineering. They cultivated a widespread public fascination with space travel, transforming it from an obscure scientific concept into an exciting and seemingly plausible future human endeavor. They inspired generations of future scientists and engineers, the very people who would one day turn these fantastical dreams into a hard and beautiful reality. The true intellectual and scientific groundwork for space travel was laid by a small and remarkable group of visionary thinkers in the late 19th and early 20th centuries. These were the true fathers of rocketry, men who, often working independently and against considerable public and scientific ridicule, developed the fundamental theoretical principles of astronautics. The first, and in many ways the most important of these, was Konstantin Tsiolkovsky, a largely self-taught and profoundly deaf Russian school teacher, working in relative and often impoverished isolation in the late 1800s and early 1900s. Tsiolkovsky, with a stunning and almost preternatural clarity, laid out the entire theoretical blueprint for space travel. He famously and correctly formulated the rocket equation, a fundamental and elegant piece of mathematics that describes the change in velocity that a rocket can achieve based on the exhaust velocity of its propellant and the ratio of its initial fueled mass to its final empty mass. This equation revealed the two crucial keys to spaceflight: high exhaust velocities and a high mass ratio. Tsiolkovsky was a passionate and early advocate for liquid-fueled rockets, recognizing their superior efficiency and controllability compared to the simple, solid-fueled rockets of his time. He was the first to seriously conceptualize multi-stage rockets. The idea of shedding the dead weight of empty fuel tanks and engines during flight, a technique that is absolutely essential for achieving orbital and escape velocities. He even, with a remarkable foresight, theorized about the use of liquid oxygen and liquid hydrogen as propellants, a combination that, due to its exceptional energy density, is still used in many of our most powerful modern rockets today. But Tsiolkovsky was more than just a brilliant technical theorist. He was a deep, and in some ways, mystical, philosophical thinker. He envisioned a future for humanity that lay not on Earth, but in space. He dreamed of space stations, of lunar bases, of the colonization of the solar system, and of an ultimate human destiny among the stars. His work, though largely unknown outside of Russia during his lifetime, provided the complete and uncannily accurate theoretical foundation upon which all subsequent practical developments in rocketry would be built. Across the Atlantic, in the United States, another, and very different, kind of pioneer was at work. Robert Goddard, an American physicist, was not primarily a theorist, but a tireless, and often frustrated, hands-on experimenter. He was often ridiculed by the press, who famously and wrongly asserted in a New York Times editorial that a rocket could not work in the vacuum of space because it would have nothing to push against. But Goddard, undeterred, persisted, and in 1926, on a cold March day in a field in Auburn, Massachusetts, he achieved a monumental and historic feat: the launch of the world's first liquid-fueled rocket. The rocket, which he had nicknamed Nell, was a small and rather unimpressive-looking contraption. It flew for only 2.5 seconds and reached an altitude of only 41 feet, but it was a transformative moment. It was the Kitty Hawk of rocketry, the first tangible proof that the theoretical promise of liquid-fueled rockets could be turned into a working physical reality. Goddard continued to develop and test more powerful and sophisticated rockets throughout his career, often facing funding challenges and working with very limited resources. He was a prolific inventor, and he held patents for many of the key components of a modern rocket, including multi-stage designs, fuel pumps, and gyroscopic guidance systems. He was the man who solved, through painstaking and often dangerous trial and error, many of the practical engineering problems that Tsiolkovsky had only dreamed about. And in Germany, another key figure, Hermann Oberth, was independently exploring the theoretical possibilities of spaceflight. His 1923 book, The Rocket into Interplanetary Space, was a rigorous mathematical exploration of the principles of rocket propulsion, and it had a profound influence on a generation of German rocket enthusiasts, including a young and ambitious engineer named Wernher von Braun. Together, Tsiolkovsky, Goddard, and Oberth are rightly known as the fathers of modern rocketry. Their independent, but remarkably convergent work formed the solid theoretical and practical bedrock of astronautics. They were the ones who showed that escape velocity, the speed required to break free from a planet's gravitational pull, was not an impossible dream, but a solvable, if difficult, engineering challenge. The grim and terrible reality of the Second World War inadvertently and tragically accelerated this development. The German V-2 rocket, developed under the leadership of Wernher von Braun, was a weapon of terror, but it was also the world's first large-scale, liquid-fueled, ballistic missile, a machine that was capable of reaching the very edge of space. After the war, both the United States and the Soviet Union scrambled to capture the German rocket scientists and their advanced V-2 technology, a process that provided a significant and morally complex leap forward for their own nascent missile and space programs. The dawn of the Cold War, in the mid-20th century, then provided the final, powerful geopolitical impetus for the race to space. The launch of Sputnik, won by the Soviet Union in October of 1957, was a profound, and for many in the West, terrifying shock. It was a clear and unambiguous demonstration of Soviet technological prowess, and it ignited a fierce and desperate determination in the United States to catch up and to surpass their ideological rivals. This event led directly to the creation of the National Aeronautics and Space Administration, NASA, in 1958, a new civilian agency that would consolidate and lead America's efforts in space. The race to the moon was on, and the once fantastical dreams of the early visionary thinkers were about to become a monumental national endeavor, an endeavor that would, in the short span of a single decade, take humanity from its first tentative steps into orbit to its first giant leap onto the surface of another world. For untold millennia, the far side of the moon remained an impenetrable mystery to humanity. From our terrestrial vantage point, only one familiar face of our celestial neighbor was ever visible, a beautiful and frustrating consequence of the gravitational dance known as tidal locking. This meant that any true knowledge of the moon's other hidden hemisphere would require a monumental leap in our technological capabilities, a leap that would take us beyond the Earth's atmosphere and into the vast, dark expanse of cislunar space. The mid-20th century witnessed the beginning of this transformative era, as the burgeoning space race between the United States and the Soviet Union propelled humanity towards its first direct observations of this enigmatic lunar territory. And it was the Soviet Union, with its early and impressive lead in powerful long-range rocket technology, that would achieve this pioneering feat, providing the world with its first blurry, but profoundly significant, glimpses of the moon's unseen side. The mission that was responsible for this groundbreaking achievement was Luna 3, a small, and by today's standards, incredibly primitive robotic probe. Its launch, in October of 1959, came just 2 years after the momentous, and for the West, deeply shocking, launch of Sputnik 1, the world's first artificial satellite. The Luna 3 mission was audacious for its time. It was designed not just to orbit the Earth, but to journey 250,000 miles to the moon, to swing around it in a complex gravitational ballet, and then, if all went well, to transmit its precious photographic cargo back across the vast and empty gulf of space. Its primary objective was singular, historic, and revolutionary: to photograph the side of the moon that had never before been seen by a human eye, or indeed, by any terrestrial instrument. The design of the Luna 3 spacecraft was a marvel of late 1950s engineering, a testament to the ingenuity of the Soviet space program, but also a reflection of the severe technological constraints of the era. It was a cylindrical craft, equipped with solar panels for power and a set of simple, whip-like antennas for communication. Its most crucial and most ingenious component was its imaging system. This was not a digital camera, which had not yet been invented. It was a complex and delicate system of 2 film-based cameras, a small, onboard, automated film processing laboratory, and a miniature, television-like scanning device. The system was designed to capture a series of images on traditional photographic film. Then, in the harsh and unforgiving vacuum of space, the film would be automatically developed, fixed, and dried. Once the images were processed, a tiny flying light spot would scan the developed film, line by line, converting the variations in light and shadow into an analog, electrical signal. This signal was then transmitted, slowly and painstakingly, back to the massive radio dishes of the deep space network on Earth. This method was inherently prone to noise, to distortion, to the 1,001 things that can go wrong in a complex, automated system operating hundreds of thousands of miles from home. But it was the cutting edge of remote imaging technology for its time. The trajectory of Luna 3 was another masterpiece of early celestial navigation. It was not designed to enter a stable orbit around the Moon, but to perform a circumlunar flyby. It was launched from Earth on a direct translunar trajectory. It then used the Moon's own gravity to bend its path, to swing it around the far side, and then to fling it back towards the Earth on a long, looping, and highly elliptical orbit. This gravity assist maneuver was a clever and efficient way to achieve the desired path without the need for a large and heavy onboard rocket engine for course correction. The timing of the photographic sequence was critical. The spacecraft had to be in the right place at the right time, with the sun in the right position to illuminate the far side. On October 7th, 1959, as Luna 3 gracefully arced around the far side of the Moon, its cameras clicked and whirred, capturing 29 images of the previously unseen hemisphere. The images, once they were finally received and processed on Earth, were, by modern standards, of a shockingly poor quality. They were blurry. They were low resolution. They were streaked with static and marred by transmission artifacts. But they were, without a doubt, one of the most important and most breathtaking set of images ever taken. They were the first empirical evidence of what lay on the other side of our own Moon. And what they revealed was a landscape that was immediately and strikingly different. The familiar near side of the Moon is defined by its extensive, dark, and relatively smooth plains, the Maria. But the Luna 3 images showed a far side that was almost completely devoid of these large, dark features. Instead, it was a continuous and seemingly endless expanse of bright, rugged, and heavily cratered terrain. This was not just a minor cosmetic difference. It was a profound geological dichotomy. It suggested that the two hemispheres of the Moon had experienced vastly different evolutionary histories. The far side appeared to be an older, more ancient, and more heavily battered surface, a surface that had not been subject to the same large-scale volcanic resurfacing that had shaped the near side. This single, stunning observation sparked a revolution in lunar science. It forced a complete re-evaluation of our models of the Moon's formation, of its internal structure, and of its thermal history. The simple and long-held assumption of a uniform, symmetric Moon was shattered forever. The naming of the newly discovered features on the far side also began with these first blurry images. The Soviet scientists, in a move that reflected the national pride of their achievement, named one of the few, small, dark patches they could discern Mare Moscoviense, the Sea of Moscow. A prominent crater was named after their great visionary rocket pioneer, Konstantin Tsiolkovsky. These names were the first human brushstrokes on a canvas that had been, for all of history, completely blank. The impact of Luna 3's achievement was immense. It was a massive propaganda victory for the Soviet Union in the intense, and often bitter, Cold War space race. It was a moment of deep and almost universal awe for the public around the world, a moment that transformed the Moon from a distant, mystical object into a real, tangible, and now partially known world. And for the scientific community, it was a tantalizing and deeply provocative first glimpse into a new and unknown land, a glimpse that would ignite a decades-long and still ongoing quest to fully understand the profound and beautiful asymmetry of our own celestial companion, Celestial. The launch of Sputnik 1 in 1957 was a profound, and for many in the United States, a deeply unsettling wake-up call. The small, beeping satellite, circling the Earth every 96 minutes, was a clear and unambiguous demonstration of Soviet technological prowess, and it ignited a fierce, and often frantic, sense of urgency in the American government and public. Before Sputnik, American efforts in space were fragmented. a patchwork of competing and often uncoordinated programs within the different branches of the military, and a smaller civilian research effort led by the National Advisory Committee for Aeronautics, or NACA. The Sputnik crisis made it abundantly and painfully clear that a new, more unified, and more ambitious approach was needed. In July of 1958, President Dwight D. Eisenhower signed the National Aeronautics and Space Act into law, creating a new, powerful, and civilian-led agency, NASA. The new agency absorbed the old NACA, along with its skilled engineers and its world-class research facilities, and it was given a clear and audacious mandate to lead America's efforts in the peaceful exploration of space. The initial goal was simply to catch up to the Soviets, but this soon evolved into a much grander and more ambitious vision, a vision that would be articulated with a powerful and enduring rhetoric by a new, young president. In 1961, President John F. Kennedy, in a speech before a joint session of Congress, threw down the ultimate cosmic gauntlet. He challenged the nation to commit itself to achieving the goal, before the decade was out, of landing a man on the moon and returning him safely to the Earth. This was not just a scientific goal, it was a political and deeply symbolic one. It was a declaration of national will, a bold and risky gambit in the high-stakes, ideological battle of the Cold War. And it was a challenge that would galvanize the nation and set NASA on a course that would lead to one of the greatest and most inspiring adventures in all of human history. But before humans could take their first giant leap, a vast amount of groundwork had to be laid. The moon was still, in many ways, an unknown and dangerous world. We needed to know what its surface was like, whether it was solid enough to support a lander, what dangers it might hold. And so, before the Apollo astronauts could fly, their robotic scouts had to go first. The Ranger program was NASA's first, and often frustrating, attempt to get a close-up look at the lunar surface. The plan was simple, if brutal, to send a series of probes on a direct collision course with the moon, transmitting high-resolution television images back to Earth in the final, frantic minutes before their impact. The early Ranger missions were a string of heartbreaking failures, a testament to the immense, and often unforgiving, difficulty of early, deep space exploration. But with Ranger 7, in July of 1964, NASA finally succeeded. The probe transmitted over 4,300 close-up images, revealing the lunar terrain in unprecedented detail, and confirming that the surface was, indeed, solid enough to land on. Following the success of the Ranger impactors, NASA embarked on the much more complex and much more ambitious Surveyor program. The goal of Surveyor was not to crash, but to land, to achieve the first, controlled, soft landing on the lunar surface. Each Surveyor spacecraft was a marvel of 1960s engineering, an insect-like contraption equipped with a powerful, solid-fuel retro rocket to slow its descent, and a set of smaller, liquid-fueled Vernier engines for fine-tuned terminal guidance. In June of 1966, Surveyor 1 made a perfect, gentle touchdown on the ocean of storms, a stunning and deeply emotional success for the young space agency. It transmitted over 11,000 images of its surroundings, showing a landscape of fine-grained, sandy material littered with small rocks and pebbles. Later, Surveyor missions carried more sophisticated instruments, including a robotic arm with a scoop that could dig into the lunar soil, and an alpha scattering device that could perform a direct chemical analysis of the lunar regolith. The Surveyor program was the ultimate and successful dress rehearsal for the Apollo landings. It proved that we could land safely, and it gave us our first direct and tangible knowledge of the strange, new ground upon which our astronauts would one day walk. At the same time, the Lunar Orbiter program was systematically mapping the entire Moon from orbit, including both the near and the far sides, with a series of 5 highly successful photographic missions. The primary goal was to scout and to certify the safest and most scientifically interesting potential landing sites for the Apollo missions. The orbiters produced a comprehensive and beautiful photographic atlas of the Moon, a set of images that not only served a crucial practical purpose, but also revealed, in stunning, high-resolution detail, the full, rugged, and ancient beauty of the lunar landscape, together the Ranger Surveyor. And lunar orbiter programs were the necessary, robotic precursors to the human adventure that was to come. They were the eyes, the ears, and the hands that we sent ahead, the silent and often heroic scouts that paved the way for the first human steps onto another world. The Apollo program was not just a technological achievement. It was a human drama of immense proportions, a story of courage, of ingenuity, of sacrifice, and of profound, and often unexpected, discovery. And it was the astronauts of the Apollo missions who would become the first, and so far, only, human beings to ever see, with their own eyes, the hidden, far side of the Moon. The first of these historic journeys was Apollo 8, in December of 1968. In a bold, and at the time, deeply risky decision, NASA sent the crew of Frank Borman, James Lovell, and William Anders on a direct circumlunar flight, the first time that human beings had ever left the gravitational embrace of the Earth and traveled to another celestial body. As their spacecraft rounded the limb of the Moon, and the Earth, for the first time in human history, disappeared from view, they were greeted by a landscape that was both awe-inspiring and deeply unsettling. "It's a vast, lonely, forbidding expanse of nothing," one of the astronauts reported back to a transfixed world. "It looks like plaster of Paris." Their live television broadcasts, though grainy and in black and white, gave humanity its first shared human experience of another world. And it was on this mission, as they came around from the far side for the 4th time, that William Anders took one of the most iconic and most influential photographs in all of human history, Earthrise. The image of our own small, fragile, and beautiful blue planet rising above the stark, gray, and lifeless horizon of the Moon was a profound, and for many, a deeply spiritual moment. It was a picture that, in a single, silent frame, captured the beauty of our own world, the desolation of the Moon, and the profound and inescapable truth of our own cosmic isolation. The missions that followed, from Apollo 10's full dress rehearsal to Apollo 17's final triumphant landing, all involved multiple orbits around the Moon. And with each orbit, the astronauts were given a new and often different view of the far side. The command module pilots, who remained in orbit while their crewmates descended to the surface, Michael Collins on Apollo 11, Richard Gordon on Apollo 12, Stuart Roosa on Apollo 14, Al Worden on Apollo 15, Ken Mattingly on Apollo 16, and Ron Evans on Apollo 17 all experienced a unique and profound form of solitude. For long periods of time, they were the most isolated human beings in the history of the universe, alone in their tiny spacecraft, circling a dead world, their only connection to the 7 billion other souls of their species. A fragile radio link that was, for 20 minutes of every 2-hour orbit, completely and totally silent. As they passed behind the Moon into the radio shadow, they were truly and completely on their own. And in these moments of profound and beautiful isolation. They were the only human beings to ever see the full sunlit expanse of the far side. Their descriptions, in their mission logs and their later memoirs, are a testament to the power and the poetry of human exploration. They spoke of its stark and almost brutal beauty, of its endless and seemingly uniform sea of craters, of its profound and almost terrifying sense of ancientness. It was a world that had not been softened by the gentle hand of erosion, a world that wore the scars of its violent 4-billion-year-long history on its face. It was a world, they all agreed, that was not like home. Even the ill-fated Apollo 13 mission, a mission that was a near disaster, provided a dramatic and unintentional human encounter with the far side. After an explosion crippled their spacecraft on the way to the moon, the crew was forced to use the moon's gravity to swing them around on a free return trajectory back to Earth. For the distressed crew of James Lovell, Jack Swigert, and Fred Hayes, the long, silent pass behind the far side was a moment of immense and almost unbearable tension, a period of radio silence when they were at their most vulnerable, their most isolated, and their most uncertain of their own survival. Their experience, though not one of scientific observation, was a powerful and deeply human testament to the isolating and unforgiving nature of this hidden lunar hemisphere. The cumulative human observations from all the Apollo missions, when combined with the precise and systematic data from the robotic probes, gave us a new and much richer understanding of the moon. They confirmed, in a direct and visceral way, the profound geological asymmetry between the two hemispheres. And they gave us a new and more profound sense of our own small and precious place in the vast and often hostile cosmos. The surface of the moon is a museum of cosmic violence, a gallery of scars that tells the long and tumultuous story of the early solar system. And the largest, oldest, and most magnificent exhibit in this museum is the South Pole-Aitken Basin, a colossal impact structure on the lunar far side that is one of the largest and oldest known impact features in our entire solar system. The basin was not discovered in a single eureka moment, but was gradually and painstakingly revealed through a series of robotic missions that have, over the decades, peeled back the layers of its mystery. The first, faint hints of its existence came from the blurry 1959 images from the Soviet Luna 3 probe. But it was NASA's Lunar Orbiter and Apollo missions in the 1960s that provided the first high-resolution photographic evidence of the vast and subtle depression that marks its location. And it has been the more recent and more sophisticated missions of the late 20th and early 21st centuries that have truly brought this ancient and monumental feature into sharp focus. The basin gets its name from its location. It is centered near the lunar South Pole, and its northern rim is marked by the smaller, but still prominent, Aitken crater. Its dimensions are staggering. It is approximately 2,500 kilometers, or 1,550 miles, in diameter, a distance that would stretch from New York City to Dallas. And it is incredibly deep, ranging from 8 to 13 kilometers, or 5 to 8 miles, from its highest mountainous rim to its lowest cratered floor. It is an impact scar of truly planetary proportions, and it is ancient. Scientists estimate that the impact that created the South Pole-Aitken Basin, or SPA, occurred very early in the Moon's history, sometime between 4.3 and 4.2 billion years ago. This places its formation squarely within the late heavy bombardment, a hypothesized and still not fully understood period in the early solar system when the inner planets and their moons were subjected to an intense and prolonged fusillade of asteroids and comets. The SPA basin is, in a sense, the moon's oldest and deepest wound. The impact that created it must have been an event of almost unimaginable violence. The prevailing theory is that it was formed by the collision of a massive asteroid or comet, perhaps several hundred kilometers in diameter, traveling at a speed of tens of thousands of miles per hour. The energy released in this cataclysmic event would have been far, far greater than all of the nuclear weapons on Earth combined. It would have instantaneously vaporized, melted, and ejected a colossal amount of the moon's primordial crust, sending a shockwave of seismic energy reverberating through the entire lunar body. The most profound and scientifically significant consequence of this impact is that it is thought to have punched a hole clear through the moon's crust and to have excavated material from the deep underlying mantle. This is a discovery of immense importance, as it offers us a rare and precious natural window into the deep interior of the moon. NASA's missions have been paramount in confirming this mantle excavation hypothesis. In the 1990s, the Galileo and Clementine spacecraft, with their multispectral imagers, provided the first tantalizing hints that the floor of the SPA Basin had a different and unusual mineral composition. Then, in 1998, the Lunar Prospector mission, with its gamma-ray spectrometer, created the first global maps of the moon's elemental composition. These maps revealed a striking anomaly. The floor of the SPA Basin has a significantly higher concentration of iron and titanium than the surrounding Highland crust. These are elements that are thought to be more abundant in the denser mantle material, but the most comprehensive and most definitive. Data has come from the Lunar Reconnaissance Orbiter, or LRO, which has been orbiting the moon since 2009. LRO's suite of advanced instruments has given us an unprecedented and multifaceted view of the SPA Basin. Its laser altimeter has created a precise, three-dimensional topographic map, revealing the basin's true depth and its complex, multi-ring structure. Its radiometer has mapped the thermal properties of the surface, providing further clues to its mineral composition. And its high-resolution cameras have given us stunning, detailed images of the terrain within the basin. When all of this data is combined, a clear and consistent picture emerges. The floor of the South Pole-Aitken Basin is a unique geological province, a place where the deep and normally hidden interior of the moon has been brought up to the surface. It is a natural laboratory for studying the composition of the lunar mantle, a study that is crucial for understanding the moon's overall formation, its thermal history, and its differentiation into a layered planetary body. This is a gift of almost incalculable scientific value. It gives us a way to sample the deep interior of another world without the immense, and at present, impossible, technological challenge of having to drill tens of kilometers through its solid, rocky crust. The SPA Basin is also a place of great interest for future exploration. It encompasses the lunar South Pole, a region where, in the deep and permanent shadows of certain craters, LRO and other missions have confirmed the existence of significant deposits of water ice. This discovery has transformed our view of the moon from a bone-dry, barren world into a place with a potentially valuable and life-sustaining resource. This water ice, if it can be mined and processed, could provide drinking water, breathable oxygen, and rocket propellant for future human lunar outposts. The South Pole-Aitken Basin, with its unique, ancient geology, its window into the lunar mantle, and its proximity to these precious polar ice deposits, is, without a doubt, one of the most scientifically compelling and strategically important locations in our entire solar system. It is a place where the deep past and the potential future of lunar exploration come together in a single, magnificent, and awe-inspiring landscape. And in 2019, humanity, through the Chinese Chang'e 4 mission, took its first, historic, robotic step into this new and exciting world. A world that was, for so long, hidden from our view. The surface of the moon is a history book written in the language of craters, unlike the Earth, with its dynamic atmosphere, its flowing water, and its active plate tectonic geology. The moon is a world of profound and beautiful stasis. It has no wind, no rain, no rivers to erode its surface. Its geological engine cooled and died billions of years ago. And so, the scars of its violent past, the countless impact craters that have pockmarked its surface over the eons, have been preserved with an almost perfect and often breathtaking clarity. But this history book is not a uniform one of the most striking and most fundamental discoveries of the space age has been the profound and deeply mysterious asymmetry between the moon's near side and its far side. The near side, the face that is forever turned towards the Earth, is a world of two distinct terrains, the bright, ancient, and heavily cratered Highlands, and the dark, younger, and relatively smooth Maria. The far side, on the other hand, is an almost continuous and seemingly endless expanse of heavily cratered highlands, the great dark Maria. The seas of solidified lava that so prominently define the near side are almost completely absent. This stark dichotomy in the density of craters and in the extent of volcanic resurfacing is one of the central puzzles of lunar science and NASA's missions, from the first robotic scouts to the human explorers of the Apollo program, have been instrumental in piecing together the clues that are now allowing us to solve it. The answer to this puzzle lies deep within the moon's own hidden interior. The key is the thickness of the lunar crust. Our detailed global maps of the moon's gravity field, most notably from the Grail mission, have revealed that the crust on the far side is significantly and systematically thicker than the crust on the near side. On average, the far side crust is about 60 kilometers thick, while the near side crust is only about 30 kilometers thick. This is a profound and fundamental asymmetry, and it is thought to be a relic of the moon's very formation. In the aftermath of the giant impact that created the moon, as the debris coalesced and the moon cooled from a molten state, the Earth's immense gravitational pull and the uneven distribution of heat-producing radioactive elements may have led to this lopsided crustal structure. And this difference in crustal thickness has had a dramatic and lasting impact on the moon's geological evolution. The Maria were formed by vast outpourings of basaltic lava from the moon's deep, and at the time, still molten, mantle. On the near side, the thinner crust provided an easier path for this magma to reach the surface. The immense impacts that created the great near-side basins also created deep fractures in this thinner crust, providing ready-made conduits for the upwelling lava. The result was a series of massive volcanic flood events that filled these basins and buried the older, cratered terrain beneath them. On the far side, however, the much thicker crust acted as a formidable barrier. Even when giant impacts created vast basins, the magma from the mantle simply could not, for the most part, find its way to the surface. The far side, therefore, was largely spared from this volcanic resurfacing. Its ancient cratered highlands, the primordial crust of the moon, were preserved. It is a more pristine, and in many ways, a more honest record of the early violent history of the solar system. This story is further supported by another, subtle, but crucial, discovery. The Lunar Prospector mission, with its gamma-ray spectrometer, found that the heat-producing radioactive elements of potassium, uranium, and thorium are not uniformly distributed throughout the moon. They are concentrated in a vast geological province on the near side, a region known as the Procellarum Creep terrain. This region, with its higher concentration of internal heat sources, would have remained hotter and more volcanically active for longer, further contributing to the extensive mare-forming volcanism on the near side. The far side, being relatively depleted in these elements, would have cooled more quickly, its volcanic engine sputtering and dying out much earlier in its history. The implications of this cratered asymmetry are profound. It means that the far side of the moon is, in a very real sense, a different world. It is an older world, a more ancient world, a world that has preserved a more complete and more pristine record of the late heavy bombardment. That intense and chaotic period in the early solar system when the inner planets were subjected to a relentless fusillade of asteroids and comets. By studying the number, the size, and the distribution of the craters on the far side, and by comparing them with the ages of the rocks brought back by the Apollo astronauts from the near side, we can reconstruct the history of this bombardment with a remarkable degree of precision. This is a technique known as crater counting, and the moon, with its two distinct and beautifully preserved faces, is our primary and most valuable Rosetta Stone for deciphering the ancient and violent history of our entire solar system. The far side is not just the other side of the moon, it is a window into the deep past, a silent and beautiful testament to the fiery and creative chaos of our own cosmic origins. The lunar highlands, the bright, rugged, and ancient terrains that dominate the far side of the moon, are the oldest and, in many ways, the most important landscapes on our celestial neighbor. They are the primordial crust of the moon, a fossilized record of its fiery birth and its turbulent youth. And they hold the key to understanding not just the history of the moon, but the very process of planetary formation itself. The prevailing theory for the origin of the Highlands is the lunar magma ocean hypothesis. This theory proposes that shortly after its formation, some 4.5 billion years ago, the moon was a global molten sphere, a vast incandescent ocean of rock. As this magma ocean slowly cooled and solidified, a process of differentiation occurred. Denser minerals, rich in iron and magnesium, crystallized and sank towards the center, forming the moon's mantle and its small metallic core. Lighter minerals, however, particularly a type of feldspar known as plagioclase, crystallized and floated to the surface like a layer of creamy slag on a molten metal. Over millions of years, this buoyant, plagioclase-rich material accumulated and solidified to form a thick, global crust of a light-colored, low-density rock called anorthosite. This primordial, anorthositic crust is what we now see as the lunar highlands. This theory, which was first proposed in the 1970s, was a bold and brilliant piece of scientific inference, and it has been confirmed with a stunning degree of precision by the samples brought back from the moon by the Apollo astronauts. The rocks collected from the highland regions on the near side were, indeed, predominantly anorthosites, their great age confirming their primordial origin. The highlands are a landscape of almost unimaginable antiquity, a surface that has been preserved, largely unchanged, for over 4 billion years. And they are a landscape of almost unimaginable violence. They are saturated with impact craters, the result of a relentless and seemingly endless bombardment by asteroids and comets in the early, chaotic history of the solar system. The surface of the highlands is not made of pristine, solid bedrock. It is a deep and thoroughly pulverized layer of regolith, a mixture of fine dust, broken rock fragments, and small, glassy beads that have been formed by the immense heat and pressure of countless impacts. And beneath this regolith lies a thick layer of breccia, a type of rock that is itself composed of the angular, cemented together fragments of older, shattered rocks. The highlands are a landscape that has been broken and rebroken again, a testament to a history of violence that is almost beyond our comprehension. And yet, it is precisely this violent history that makes the highlands so scientifically valuable. They are a pristine and beautifully preserved record of the late heavy bombardment. By studying the craters of the highlands, we can learn about the size, the number, and the nature of the objects that were careening through the early solar system. This is information that is crucial for understanding how the planets themselves formed, and how our own home world, the Earth, survived this early and very dangerous period of its life. The Earth, too, must have been subjected to this same intense bombardment, but on our dynamic and geologically active planet. The evidence of this ancient history has been almost completely erased, wiped clean by the relentless processes of plate tectonics, of volcanism, of erosion. The Moon, in its beautiful and silent stasis, has preserved the story that the Earth has forgotten. It is our celestial attic, our planetary memory, a place where the deep and often violent secrets of our own cosmic family are stored, the persistent and deeply ingrained. Popular misconception of a dark side of the Moon is a beautiful example of how a simple linguistic ambiguity can lead to a profound and enduring scientific misunderstanding. The term dark side has a powerful and almost mystical resonance. It conjures up images of a perpetually shadowed and mysterious hemisphere, a realm of eternal night. But the reality is far more mundane, and in many ways, far more interesting. The Moon does not have a dark side, it has a far side. And the far side is not perpetually dark. It experiences a regular and predictable cycle of day and night, just like the near side, and just like our own Earth. The confusion arises from the phenomenon of tidal locking, because the Moon's rotation is synchronized with its orbit. The same hemisphere, the near side, is always facing the Earth. The other hemisphere, the far side, is therefore always facing away from us. It is dark in the old-fashioned sense of being unknown, of being hidden from our view. But it is not dark in the sense of being unlit. The source of light in our solar system is the Sun, not the Earth. And as the Moon orbits the Earth, it is also, of course, orbiting the Sun over the course of a single lunar day. A period of about 29.5 Earth days, the Sun's light sweeps across the entire spherical surface of the Moon. Every part of the Moon, both the near side and the far side, experiences about 2 weeks of continuous, brilliant daylight, followed by 2 weeks of deep, cold, and continuous night. The phases of the Moon, as seen from Earth, are a direct consequence of this changing illumination. When we see a new moon, the Moon is positioned between the Earth and the Sun. The side of the Moon that is facing us, the near side, is in darkness. But at that very same moment, the far side of the Moon is fully illuminated, basking in the light of its own high noon. Conversely, when we see a full moon, the Earth is positioned between the Sun and the Moon. The near side is fully illuminated, and at that moment, the far side is in the midst of its long, 2-week-long night. The first, definitive, and human confirmation of this simple but profound astronomical fact came with the Apollo 8 mission in December of 1968. As the astronauts became the first human beings to ever orbit the Moon, their television camera, broadcasting back to a transfixed world, showed them the sunlit and deeply cratered landscape of the far side, and the iconic Earthrise photograph, taken on that same mission, is a beautiful and powerful testament to this reality. The image shows our own blue and white planet, rising above a stark, gray, and clearly sun-drenched lunar horizon. The landscape in the foreground of that photograph is on the far side of the Moon. The only places on the Moon that are truly perpetually dark are the deep and frigid floors of certain craters at the lunar poles, because of the Moon's very small axial tilt. The Sun is always very low on the horizon at the poles. This means that the floors of some deep craters are forever shielded from the direct rays of the Sun. These permanently shadowed regions are some of the coldest places in our entire solar system. And it is in these cold, dark traps that the moon has been hiding its most precious and most surprising secret. For most of the 20th century, the scientific consensus was that the moon was a bone-dry and completely waterless world. The rock samples brought back by the Apollo astronauts, when first analyzed, seemed to confirm this view. They were found to be almost completely devoid of water. This dry moon paradigm had a profound and chilling effect on our plans for future human exploration. It meant that any long-term human presence on the moon would be an immense and costly logistical challenge, requiring all the necessary water for drinking, for life support, and for growing food to be ferried, at great expense, from the deep gravitational well of the Earth. But in the last few decades, this paradigm has been completely and beautifully overturned. A series of sophisticated robotic missions, many of them led by NASA, has revealed that the moon is not as dry as we once thought. In the deep, dark, and permanently shadowed craters at its poles, it is hoarding a vast and potentially invaluable reservoir of water ice. The first tantalizing hints came in the 1990s from the Clementine and Lunar Prospector missions. These orbital probes, using radar and a neutron spectrometer, detected the telltale signatures of hydrogen concentrated in the polar regions. The most plausible form for this hydrogen, in these incredibly cold, permanently shadowed environments, was water ice. But the definitive, smoking gun proof came in 2009 with NASA's spectacular and deliberately destructive L-Cross mission. The mission involved intentionally crashing a spent Centaur rocket stage into a permanently shadowed crater at the moon's south pole. A second shepherding spacecraft then flew through the plume of debris that was kicked up by the impact, analyzing its composition with a suite of onboard instruments. The data was unambiguous. The spectrometers on the shepherding spacecraft detected the clear and unmistakable spectral signatures of both water vapor and water ice. The water was real. The discovery of water on the moon is a true game changer. Water is the single most important resource for supporting a long-term human presence in space. It can be used for drinking and for growing food. It can be split through electrolysis into its constituent elements, hydrogen and oxygen. The oxygen can be used for breathable air, and the hydrogen and oxygen, when recombined, are a powerful and clean rocket propellant. The moon, it turns out, has its own built-in gas station. The ability to mine and to utilize this lunar water, a process known as in situ resource utilization, or ISRU, is the key to creating a sustainable and ultimately a self-sufficient human presence on the moon. It is the key to breaking our complete and costly reliance on the Earth for all of our resources. It is the key that will unlock the door to a future where the moon is not just a place we visit, but a place where we live, and a place from which we can journey onwards to Mars and beyond. The discovery of water on the moon has transformed our nearest celestial neighbor from a barren geological museum into a dynamic and strategically important new frontier. A frontier that is rich with both scientific mystery and profound human possibility. The moon's gravitational field is not the smooth, uniformed, and perfectly spherical field of a textbook problem. It is a lumpy and complex gravitational landscape, a landscape of subtle hills and valleys that is a direct reflection of the uneven distribution of mass within the moon's interior. These gravity anomalies were first discovered serendipitously in the 1960s, when the mission controllers for NASA's Lunar Orbiter and Apollo missions noticed that their spacecraft were being mysteriously and frustratingly tugged off course as they orbited the moon. These unexpected orbital perturbations were caused by localized regions of unusually strong gravitational pull, regions that were quickly and evocatively dubbed masscons, for mass concentrations. The most prominent of these masscons were found to be associated with the large, circular, mare basins on the near side. This was a deep, and at the time, completely unexpected puzzle. These basins are the lowest points on the lunar surface. Why should they be the location of a large, excess mass? The answer, we now know, lies in a combination of two effects. The immense impacts that created these basins not only excavated a huge amount of the low-density crustal material, but they also caused the denser underlying mantle material to rebound upwards, closer to the surface. And then, these thinned-out basins were filled with a thick and very dense layer of basaltic lava. It is this combination of a raised, dense mantle and a thick, dense lava fill that creates the strong, positive gravity anomaly of the masscons. The fact that these masscons are still there, that they have not been erased by the slow, isostatic adjustment of the lunar crust over billions of years, tells us something profound about the moon's interior. It tells us that the moon's outer, solid layer, its lithosphere, has been very thick and very rigid for a very long time. It cooled and solidified much more quickly than the Earth's, and it has been for most of its history, a geologically dead and unyielding world. The far side, with its almost complete lack of large maria, also, unsurprisingly, lacks these large, prominent masscons. Even the colossal South Pole-Aitken Basin does not have a strong, positive masscon. Its gravity signature is more subtle and more complex, a reflection of its different and more ancient history. But the most detailed and most beautiful map of the moon's gravity field has come from NASA's Grail mission. In 2011, two identical spacecraft, named, charmingly, Ebb and Flow, were placed in a close, tandem orbit around the moon by precisely and continuously measuring the tiny changes in the distance between the two spacecraft as they orbited, to an accuracy of a few microns. The mission was able to create an incredibly high-resolution map of the entire lunar gravity field. The map is a work of scientific art. It reveals not just the large masscons, but a wealth of smaller and more subtle anomalies associated with individual craters, with buried volcanic structures, and with the deep tectonic faults of the lunar crust. It is a new and powerful way of seeing the moon, an X-ray vision that allows us to peer beneath the surface and to map the hidden and complex architecture of its interior. The moon today does not have a global magnetic field. It lacks the hot convecting and electrically conducting liquid outer core that is required to generate a planetary dynamo, the kind that creates the Earth's protective magnetosphere. And yet, the moon is not entirely non-magnetic. The rock samples brought back by the Apollo astronauts were found to be surprisingly and mysteriously magnetic. And our orbital probes have detected a series of weak, localized, and patchy magnetic anomalies embedded in the lunar crust. These are fossil magnetic fields, the frozen and ghostly remnants of a time long ago when the moon was a very different and much more dynamic world. The existence of these remnant magnetic fields is a profound and beautiful clue. It tells us that in its distant past, for a period of at least 1 billion years, the moon did have a global magnetic field. It did have a hot, molten, and convecting core. It did have a dynamo. This discovery has revolutionized our understanding of the moon's thermal history, showing us that it was not a simple, cold, and inert body, but a true, and for a time, a geologically active planet. The distribution of these fossil magnetic fields is also deeply strange. They are much stronger and much more prevalent on the far side of the Moon than on the near side. And some of the strongest of these far-side anomalies are found in a very peculiar and very specific location at the Antipode, the point on the Moon's surface that is diametrically opposite to the large, young, and near-side impact basins, like Mare Imbrium. This is a stunning and deeply suggestive correlation, and it has led to a beautiful and compelling theory. The idea is that the immense energetic impacts the UAT created these near-side basins sent a powerful and highly focused seismic shockwave reverberating through the entire, and at the time, still molten, body of the Moon. When this shockwave converged at the Antipode, on the far side, it created a region of intense, localized heating, and perhaps even melting of the crustal rock. As this rock then cooled and solidified, in the presence of the Moon's ancient global magnetic field, it became strongly and permanently magnetized. The impact, in a sense, acted as a cosmic recording head, imprinting the signature of the global magnetic field onto the crustal rock at its antipode. And these ancient magnetic memories are not the only strange and beautiful feature of the lunar surface. There are also the lunar swirls, strange, sinuous, and bright patterns that are found in several locations on the Moon. These swirls are not associated with any topographic features. They are like delicate and ghostly paintings on the lunar regolith. And they are almost always found in regions of strong, localized magnetic anomalies. The leading theory is that these magnetic anomalies are acting as miniature and very weak magnetospheres, shielding the surface from the constant, darkening effect of the solar wind, and thus preserving the brighter, more pristine appearance of the underlying soil. The lunar swirls are a direct and beautiful visual manifestation of the Moon's hidden and fossilized magnetic past, the story of the Moon. As revealed by our decades-long and still ongoing scientific exploration, is a story of profound and beautiful asymmetry. It is a tale of two very different worlds bound together in a single celestial body. The near side is a world of dramatic contrasts, of dark, volcanic Maria and bright, ancient Highlands, a world whose face has been shaped and reshaped by a long and complex history of both internal geological activity and external cosmic bombardment. The far side is a more ancient, more uniform, and in many ways a more honest world, a world that has been largely spared from the resurfacing effects of volcanism, a world that has preserved, with a stark and beautiful clarity, the deep and violent scars of its own primordial past. This fundamental dichotomy is not just skin deep. It is a reflection of a deep and enduring asymmetry in the Moon's very structure, in the thickness of its crust, in the distribution of its internal heat, and in the fossilized remnants of its ancient magnetic field. And it is a story that has been painstakingly and beautifully pieced together by a long and heroic series of scientific missions that have taken us from our first, blurry and ghost-like glimpses of the hidden side to the detailed, high-resolution, and multifaceted understanding that we have today. The once hidden, far side of the Moon is no longer a blank page in our cosmic atlas. It is a rich and complex and beautiful new chapter. A chapter that is not just about the Moon, but about the deep, and often violent, history of our entire solar system, and about our own small and precious place within it. The journey to the Moon has not just been a journey to another world. It has also, and always, been a journey home. A journey that has given us a new and more profound appreciation for the beauty, the fragility, and the sheer cosmic good fortune of our own, blue and white, and very much alive, planet Earth. You are aboard a spacecraft, floating in the silent, inky abyss of interstellar space. The stars outside your window are ancient, their light having stretched across millions of years to reach your eyes. Every movement, every signal sent from your ship takes time to travel minutes, hours, even years to cross the cosmic void. But then, something impossible happens. A message appears on your screen, not carried by radio waves, not transmitted through light, but teleported. Its information woven into the very fabric of quantum reality. It did not travel the distance between its origin and your ship. It simply appeared. This is not a scene from science fiction. It is the strange and beautiful reality of quantum teleportation, a process where information, not matter, is transferred instantaneously, breaking the traditional rules of space and time. Unlike the teleporters of futuristic movies, quantum teleportation does not transport objects or people, but rather the very essence of their quantum state, the fundamental, informational blueprint that defines them. But how is this possible? How can something leap across space without physically moving? To answer this, we must journey into the depths of quantum mechanics, into a world where particles can exist in multiple states at once, where entanglement links objects across vast cosmic distances, and where reality itself appears to be nothing more than a fragile, shimmering web of probabilities. This is the story of quantum teleportation, a phenomenon that challenges the very nature of existence, a discovery that could one day revolutionize communication, computing, and perhaps even our understanding of the universe itself. But before we can unlock the secrets of teleportation, we must first understand the bizarre, counterintuitive, and wonderfully mysterious quantum world that makes it all possible. There was a time, not so long ago, when physics was simple. The world was a clockwork universe, a grand deterministic machine where objects had precise locations, forces acted predictably, and the future was, in principle, calculable from the present. But at the dawn of the 20th century, this elegant, common-sense picture began to crumble. The quantum revolution arrived, a theory so strange, so counterintuitive, so profoundly weird, that even its own architects, like Albert Einstein, struggled to accept its full implications. At the heart of this revolution lies a disturbing and beautiful truth at the smallest scales. The universe does not behave in any definite way until we observe it. To understand why this is so profound, picture a simple marble rolling across a smooth table. In the classical world of our everyday experience, if you knew its exact position and its exact velocity, you could predict its entire future trajectory with perfect certainty. But in the quantum world, this certainty dissolves. The quantum marble, an electron, for example, does not have a single, definite position. It exists as a wave of probability, a diffuse cloud of potential locations, a superposition of all the places it could possibly be. It is not here or there. It is, in a very real sense, both here and there, and everywhere else in between, all at the same time. It is only when an observer looks, when a measurement is made, that this shimmering cloud of possibilities collapses, and the electron chooses a single, definite location. This is not just a mathematical trick or a philosophical abstraction. It is an experimental fact, one that has been confirmed time and time again. The famous double-slit experiment demonstrates this with an almost mystical clarity. When a beam of electrons is fired at a barrier with two narrow slits, and we do not try to determine which slit each electron passes through, An interference pattern appears on a detector screen behind the barrier. This pattern of alternating bright and dark bands is the classic signature of waves interfering with each other, like the ripples from two stones dropped in a pond. This happens even if the electrons are fired one at a time. Each individual electron seems to pass through both slits simultaneously, as a wave, and then interfere with itself. But the moment we place a detector at one of the slits to watch which path the electron takes, the wave-like behavior vanishes. The interference pattern disappears, and we see two simple bands on the screen, corresponding to the two slits. The electron now behaves like a well-behaved particle, choosing one path or the other. The very act of measurement, of gaining information, has changed the nature of reality itself. But if the principle of superposition is strange, the phenomenon of quantum entanglement is stranger still. Imagine two particles, born from the same quantum event, their fates forever intertwined. They fly apart, separated by miles, by light years, by the vast expanse of the cosmos. And yet, they remain connected by an invisible, instantaneous thread. This is quantum entanglement, a phenomenon so bizarre that Einstein famously called it spooky action at a distance. Entanglement means that two particles, no matter how far apart, are no longer independent entities, but are part of a single, unified quantum system. If you measure a property of one particle, say its spin, and find it to be clockwise, you instantly know, with absolute certainty, that its entangled partner, on the other side of the galaxy, will be found to be counterclockwise if you were to measure it. This instantaneous correlation seems to defy one of the most fundamental principles of physics, that no information can travel faster than the speed of light. Einstein was convinced that this spooky action was a sign that quantum mechanics was an incomplete theory. He believed that there must be some hidden variables, some unseen, predetermined properties of the particles that were secretly guiding their behavior. The particles, in his view, were like a pair of gloves, separated into two boxes. The moment you open one box and find a left-handed glove, you instantly know the other contains a right-handed one, not because of some spooky, faster-than-light communication, but because their states were determined from the very beginning. For decades, this was a philosophical debate. But in 1964, the physicist John Bell devised a brilliant mathematical theorem that transformed this debate into an experimental question. Bell's theorem established a set of inequalities that would have to be satisfied if any local hidden variable theory, like Einstein's, were correct. Quantum mechanics, on the other hand, predicted a clear violation of these inequalities. The stage was set for a definitive test of the nature of reality. And when the experiments were finally performed, with increasing precision over the decades, the results were undeniable. Bell's inequality was violated, time and time again. The universe is not locally real. The spooky action is real. The predictions of quantum mechanics, in all their strange and beautiful glory, were confirmed. This revelation was profound. It meant that at its core, the universe is not governed by the rigid, deterministic laws of classical physics, but by the strange, probabilistic, and deeply non-local rules of the quantum world. A particle's properties are not fixed until they are measured, and once measured, entangled particles seem to communicate their states instantaneously, in a way that defies our classical understanding of space itself. And it is this very spookiness, this non-local connection, that provides the key to one of the most revolutionary concepts in all of science, quantum teleportation. Teleportation is not about physically moving an object from one place to another. It is about transferring its quantum state, the very essence of its identity, the complete informational blueprint that describes its properties, without sending the object itself. And to do this, we must use the strange and powerful magic of entanglement. The process of quantum teleportation is a delicate and beautiful dance of quantum principles. It is a process that seems, at first glance, to be a paradox, a violation of the very laws it relies on. But upon closer inspection, it is a stunning testament to the strange and beautiful logic of the quantum world. The process begins with an essential ingredient, a pair of entangled particles. Let's call them particle A and particle B. These two particles are created in such a way that their quantum states are perfectly correlated. One of these particles, A, is kept at the sender's location. The other, B, is sent to the receiver, who may be light years away. Now, a third particle, let's call it particle C, is introduced. This is the particle whose quantum state we want to teleport. Particle C is brought into contact with the sender's entangled particle, A, and a special joint measurement is performed on them. This measurement, known as a Bell state measurement, does something remarkable. It forces the combined system of A and C into one of four possible entangled states, and in doing so, it has a profound and seemingly destructive consequence. The original quantum state of particle C is completely erased. It no longer exists at the sender's location, but the information has not been lost. It has, in a sense, been imprinted onto the distant, entangled particle, B. At this moment, the receiver's particle, B, has absorbed the quantum information from particle C, but it remains in a scrambled, incomplete form to complete the teleportation. A final crucial step is required. The sender must communicate the result of their Bell state measurement, a simple 2-bit piece of classical information, to the receiver. This message must travel through normal space, at or below the speed of light. Once the receiver has this classical information, they know which of the four possible outcomes occurred at the sender's end, and they can perform a specific, simple transformation on their particle, B. And with that final touch, particle B becomes a perfect, identical replica of the original particle C, possessing the exact same quantum state that was destroyed at the sender's end a moment before. The teleportation is complete. The information has been transferred. But what makes this process so strange and so profound is that nothing physical has traveled between the two locations. The quantum state did not move through the intervening space. The particle at the receiver's end was never in physical contact with the original. And yet, somehow, the exact and incredibly fragile quantum information has been perfectly reconstructed, as if by magic. This raises a deep and fundamental question. Where was the information during its journey? One interpretation is that quantum states are not localized entities at all. They are non-local patterns of probability spread out across space-time. In this view, teleportation is not a process of movement in the classical sense, but is a rearrangement of this non-local information, a shifting of the quantum state from one physical carrier to another, a process that is not constrained by the normal rules of spatial separation. Another, related perspective comes from the framework of quantum field theory, which, as we have seen, suggests that particles are just excitations of an underlying universal quantum field. In this view, teleportation is not about moving a thing from point A to point B, but is an operation on the field itself, a process that causes the quantum state to de-manifest at one location and re-manifest at another. Regardless of the interpretation, one thing is clear: quantum teleportation, while seemingly instantaneous at the quantum level, does not allow for faster-than-light communication. The need to transmit the classical information about the measurement outcome ensures that the overall process is always limited by the speed of light, preserving the sacred principle of causality and keeping Einstein's theory of relativity intact. But this does not make the process any less remarkable. Quantum teleportation is a direct and powerful demonstration of the deeply non-local nature of reality. It is a process that is only possible because the universe, at its core, is not a collection of separate, independent objects, but a single, holistic, and entangled system. And it is a process that has already been achieved in laboratories around the world. Scientists have successfully teleported the quantum states of photons, of atoms, and even of small molecules over increasingly large distances. The future of this technology is one of incredible promise. It is the key to building a secure, unhackable quantum internet. It is the foundation for creating large-scale, distributed quantum computers. And it is a powerful tool for probing the very nature of reality itself. But as we stand on the threshold of this new quantum informational age, we are also forced to confront some of the deepest and most unsettling questions about our own existence. If the very essence of a particle, its informational soul, can be erased and reborn elsewhere, what does that mean for our own human sense of identity, of continuity, of the self? The strange magic of quantum teleportation is not just a technological trick. It is a profound and deeply philosophical challenge to our most cherished assumptions about what it means to be real. The question of whether quantum teleportation could one day be applied to a human being is one that pushes the boundaries of science, of ethics, and of philosophy. It is a question that forces us to confront the very nature of our own identity, of our consciousness, of the self. At first glance, the idea seems like the ultimate science fiction dream: to step into a machine, to be dematerialized, and to be instantaneously reconstructed on a distant planet, a perfect copy of your former self. But the quantum reality of teleportation is far stranger and far more unsettling than this simple picture would suggest. The first and most crucial thing to understand is that quantum teleportation does not transport matter. It transports information. To teleport a human being, you would not be sending their atoms across space. You would be scanning the complete quantum state of every single particle in their body, an almost infinitely complex task, destroying the original in the process, and then using that information to reconstruct a new body, atom by atom, at the destination. This is not a process of movement. It is a process of destruction and recreation. And this is where the profound and deeply troubling philosophical problems begin. The no-cloning theorem of quantum mechanics, as we have seen, states that it is impossible to create a perfect, identical copy of an unknown quantum state. This means that if you were to be teleported, there could be no backup copy of you. The original you, the one who stepped into the machine, would have to be destroyed for the new you to be created. The process is one of replacement, not duplication. So, is the person who emerges at the other end still you? From a purely physicalist or functionalist perspective, the answer might be yes. If consciousness is nothing more than a complex pattern of information, a specific arrangement of neural connections and quantum states in the brain, and if that pattern is perfectly replicated, then the subjective experience of consciousness should, in theory, continue seamlessly. The new you would have all the same memories, the same thoughts, the same feelings, the same sense of self. For them, it would be as if they had simply closed their eyes in one place and opened them in another. But this is where the thought experiment of a malfunctioning teleporter becomes so powerful and so disturbing. Imagine the machine scans you, transmits your information, and reconstructs you at the destination. But due to a glitch, it fails to destroy the original you. Now there are two of you. Both are physically identical. Both have the same memories. Up until the moment of teleportation, both believe, with absolute conviction, that they are the real you. Which one is right? Who has the claim to your life, to your relationships, to your past? This scenario highlights a deep problem with a purely functionalist view of identity. It suggests that there may be something more to the self than just a pattern of information. There is also the issue of continuity of consciousness. We have a powerful, intuitive sense that our self is a continuous, unbroken stream of experience, a single thread that runs from our birth to our death. The process of teleportation, of destruction and recreation, seems to violently sever this thread. Would the original you experience a moment of annihilation, a final terrifying end? And would the new you just be a perfect, but ultimately soulless copy, a philosophical zombie that looks and acts just like you, but has no genuine, inner, subjective experience? Some theories of consciousness, like the orchestrated objective reduction model, suggest that this might indeed be the case. If consciousness is a real physical or quantum process that is tied to the specific physical structure of the brain, then it may not be something that can be simply copied and pasted into a new physical substrate. The delicate quantum coherence that gives rise to our subjective experience might be a unique and non-transferable property of our original biological brain. In this view, the teleported you would be a perfect physical replica, but it would be an empty shell, a being without a soul. But even if we set aside these more exotic theories of consciousness, the very nature of time and perception in the teleportation process raises a host of unsettling questions. If the reconstruction process at the destination is delayed by 10 minutes, what does the teleported person experience? Do they exist in a state of nothingness for those 10 minutes? Or do they experience an instantaneous jump forward in time, a gap in their subjective experience that they can never account for? And what if the reconstruction process fails entirely? If the original you is destroyed, but the new you is never created? Have you died, or from your own subjective perspective, have you simply ceased to exist at a particular moment, with no experience of death at all? These are not just scientific questions. They are deep, existential riddles that touch on the very meaning of what it means to be alive, to be a person, to have an identity. If teleportation were ever to become a reality for human beings, it would force a profound, and perhaps painful, re-evaluation of our most deeply held beliefs about the self. It could lead to a new and more fluid understanding of identity, where the self is not a fixed, singular entity, but a pattern that can be moved, that can be stored, that can perhaps even be branched. It could open up the possibility of a new kind of immortality, where our minds are not tied to a single, fragile, biological body, but can be backed up, transferred, and restored. But it would also open up a Pandora's box of new and deeply challenging ethical and social dilemmas. The question of teleportation is not just about whether we can do it. It is about whether we should. And it is a question that forces us to confront the possibility that our cherished and seemingly solid sense of a continuous, singular self is just a fragile and beautiful illusion. An illusion that the strange and powerful magic of quantum teleportation threatens to expose. The paradox of a malfunctioning teleporter, the scenario where an original and a copy of a person coexist, leads us down a rabbit hole of even deeper and more mind-bending quantum possibilities. It forces us to confront the idea of quantum immortality, a strange and unsettling consequence of the many worlds interpretation of quantum mechanics. In the many worlds view, as we have seen, every quantum event causes the universe to split into multiple parallel branches, with each branch corresponding to a different possible outcome. If a teleportation machine has even a minuscule 1 in a trillion chance of malfunctioning and failing to destroy the original, then in the vast branching tree of the multiverse, there must be a branch where this failure occurs. From an external, the third-person perspective, the vast majority of teleportation events are successful. The original is destroyed, the copy is created, and the process works as intended. But what about from the first-person, subjective perspective of the person stepping into the machine? This is where the idea of quantum immortality comes in. The theory suggests that your consciousness, your subjective stream of experience, will always and only follow the branches of the multiverse where you survive. You can never, by definition, experience a reality in which you have ceased to exist. So, if there is a branch of reality where the teleporter malfunctions and the original you is not destroyed, then your consciousness must, according to this theory, follow that branch. From your perspective, you would step into the teleporter. The machine would whir and hum, and then nothing would happen. You would emerge, unscathed, to be told by a surprised scientist that the teleportation had failed, but that a perfect copy of you had, in fact, been created at the destination. For the rest of the world, there are now 2 of you. But for you, the original, your stream of consciousness has remained unbroken. This has a truly bizarre and deeply unsettling implication. It suggests that from your own subjective point of view, you can never die in a teleportation event. You will only ever experience the realities in which you survive. It is a form of personal, probabilistic immortality. This idea can be extended beyond teleportation to any life-threatening event. If you are in a car crash and there is even a tiny, non-zero quantum probability that you will swerve at just the right moment to survive, then, in the many worlds picture, there is a branch of reality where you do, and your consciousness will follow that branch. Everyone in the other branches will mourn your tragic death, but you will experience a miraculous and seemingly impossible escape. Over the course of a long life, a person who believes in quantum immortality would find themselves living a charmed and increasingly improbable existence, surviving against all odds, a living testament to the fact that their consciousness is always and only on the winning side of the cosmic quantum coin toss. This is a strange and deeply counterintuitive idea, and it is one that is, of course, highly speculative and untestable. But it is a logical consequence of taking the many worlds interpretation of quantum mechanics seriously. And it completely reframes our understanding of what teleportation would mean for the self. It would not be a simple process of movement from A to B. It would be a process of branching, of creating new versions of reality. Every time you step into a teleporter, you are not just traveling. You are playing a game of quantum Russian roulette, a game in which, from your own perspective, you can never lose. But what does this do to our sense of identity? If there are an infinite number of yous branching off with every quantum event, which one is the real you? The many worlds interpretation suggests that they are all equally real. Identity is not a single, continuous thread, but a vast and ever-growing, branching tree. This is a vision of the self that is far more fluid, more multiplicitous, and more deeply connected to the probabilistic nature of the cosmos than our classical intuition would ever allow. The implications for human society would be profound. How would our legal systems deal with the existence of multiple identical copies of a person who would be responsible for the actions of a branched self? How would our concepts of love, of family, of inheritance be transformed in a world where identity is no longer singular? The psychological impact would be equally staggering. Would the knowledge that you are constantly branching into other realities lead to a sense of existential liberation, or to a profound and dizzying sense of personal dissolution? Would people embrace the fluid, branching nature of the self, or would they cling, with even greater desperation, to the illusion of a single, stable identity? And what about the ethics of teleportation itself? If every use of a teleporter creates a new branch of reality, are we, in a sense, polluting the multiverse with an endless proliferation of copies? These are questions that are on the very frontier of our scientific, philosophical, and ethical thinking. They are questions that are born from the strange and beautiful marriage of our most advanced physical theories with our deepest and most enduring questions about the nature of the self. Quantum teleportation, in this light, is not just a technological dream. It is a philosophical mirror, a tool that reflects back to us the deep and often unsettling quantum nature of our own human existence. It forces us to confront the possibility that we are not the solid, singular, and continuous beings we believe ourselves to be, but are something far stranger, more fluid, and more wonderfully mysterious of branching, probabilistic, and perhaps even immortal wave of consciousness, forever surfing the crest of an infinite quantum sea. The strange and powerful phenomenon of quantum teleportation does not just challenge our understanding of space, it also, and perhaps even more profoundly, challenges our understanding of time, our classical. Everyday intuition tells us that time is a one-way street, a river that flows inexorably from a fixed past, through a fleeting present, to an open future. But the quantum world, with its non-local connections and its probabilistic nature, seems to hint at a more complex and more mysterious temporal reality. And quantum teleportation may be the key that allows us to unlock its secrets. At its core, teleportation is about the transfer of quantum information, and this information, as encoded in the state of an entangled system, seems to exist outside the normal constraints of space. The connection between two entangled particles is instantaneous, regardless of the distance between them. But if this connection can transcend space, could it also transcend time? Could quantum teleportation be used not just to send a message across the galaxy, but also to send a message back to yesterday? This is a radical and deeply challenging idea, but it is one that is not entirely ruled out by the laws of quantum mechanics. The equations of quantum mechanics are, for the most part, time-symmetric. They work just as well for a process running backwards in time as they do for one running forwards. This has led some physicists to speculate that the non-local connection of entanglement may not just be a spatial one, but a temporal one as well. Two particles could be entangled in time, with a measurement on a particle in the future having an instantaneous effect on the state of a particle in the past. The famous delayed choice quantum eraser experiment is a stunning and deeply perplexing demonstration of this kind of apparent backward-in-time influence. In this experiment, the choice of whether or not to measure the witch path information of a photon seems to retroactively determine whether that photon behaved as a particle or a wave in the past. It is as if a decision made in the present can reach back and change the nature of a past event. This does not mean that we can send a controllable message back in time to change history. But it does suggest that the relationship between the past, the present, and the future at the quantum level is far more subtle, more holistic, and more mysterious than our classical intuition would ever allow. Could quantum teleportation be used to harness this strange temporal non-locality? Imagine a scenario involving entanglement swapping. You can take two independent pairs of entangled particles, and by performing a specific joint measurement on one particle from each pair, you can swap the entanglement so that the two previously unconnected particles from the different pairs become entangled with each other. Now, what if one of these entangled pairs was created in the distant past? and the other is created in the present. By performing an entanglement swap, you could, in theory, create an entangled link between a particle that exists now and a particle that existed then. You would have created a quantum channel that connects two different points in time. Could this channel be used to teleport a quantum state from the present to the past? This is a highly speculative and technically challenging idea, but it is one that is being seriously explored by some theoretical physicists, and it opens up the breathtaking possibility of a new kind of time travel. A time travel not of physical objects, but of pure quantum information. This would be a form of time travel that could potentially bypass some of the famous paradoxes of classical physical time travel. You could not go back and kill your own grandfather because you cannot teleport a macroscopic object. But you might be able to send a single qubit of information back, a quantum message that could perhaps influence the probabilities of past events. But even if such a process were possible, the universe may have its own built-in chronology protection mechanisms. The self-consistency principle, proposed by physicists like Igor Novikov, suggests that even if time travel is possible, the laws of physics will conspire to prevent any paradoxes from occurring. Any action you take in the past will be, in a sense, self-consistent. If you were to send a message back in time to warn yourself not to step into the street and get hit by a bus, something would have to happen to prevent you from receiving or acting on that message. The bus would still hit you. The outcome would be consistent with the fact that you were there in the future to send the message in the first place. The many worlds interpretation of quantum mechanics offers another, and perhaps more elegant, solution. If you were to send a quantum state back in time, you would not be sending it back into the past of your own universe. You would be sending it to a different parallel branch of the multiverse. You could change the past in that universe, but it would have no effect on your own. Personal history. The timeline would remain consistent because you have simply created a new and different one. The deep and mysterious connection between quantum teleportation and the nature of time is a frontier of scientific inquiry that is still in its infancy. But it is a frontier that is full of profound and potentially revolutionary possibilities. It is a frontier where the strange, non-local magic of the quantum world seems to touch upon the deepest and most enduring mysteries of our own temporal existence. Is it possible that our own consciousness, with its strange and often non-linear relationship with time, is a macroscopic manifestation of these deep quantum temporal effects? Could our flashes of intuition, our moments of déjà vu, our precognitive dreams be the result of our brains as quantum systems, tapping into the subtle temporal entanglements of the universe? These are speculative questions, to be sure, but they are questions that are no longer just the domain of the mystics and the philosophers. They are questions that are beginning to be asked in a new and more rigorous way by the physicists who are probing the very heart of quantum reality. Quantum teleportation has shown us that our classical, intuitive understanding of space is a profound illusion, and it may be that its greatest and most unsettling. Revelation is still to come that our classical, intuitive understanding of time is an illusion as well. The strange, non-local, and instantaneous nature of quantum teleportation does more than just challenge our classical notions of space and time. It forces us to confront an even more radical and more profound possibility that the universe itself is a vast, interconnected teleportation network. In this vision, space is not a fundamental, empty void that separates objects, but is an emergent illusion, a macroscopic manifestation of a deeper and more fundamental level of quantum informational connectivity. The universe is not a collection of separate things. It is a single, holistic, and entangled system, where every part is in instantaneous communication with every other part. This is an idea that has its roots in the holographic principle and the Eir-Eper conjecture, which, as we have seen, suggests that the geometry of space-time is a holographic projection of the underlying quantum entanglement between its constituent parts. In this view, the universe is not in space. Space is in the universe. The seemingly vast distances between the galaxies are not a measure of a fundamental separation, but are a reflection of the weakness of the entanglement between those distant regions. Two particles that are right next to each other are strongly entangled. Two galaxies that are billions of light-years apart are very weakly entangled, but the connection is still there. If this is the case, then quantum teleportation is not a strange, anomalous process that violates the normal rules of space. It is a direct and powerful manifestation of the true, underlying, non-local nature of reality. It is not about sending information across space. It is about accessing the hidden, informational pathways that are the very fabric of space itself. This would mean that our current and technologically challenging methods of teleportation, which rely on the creation and distribution of entangled particle pairs, are just a clumsy and very inefficient way of tapping into a universal process that is happening naturally and continuously at every point in the cosmos. This vision of a teleportation universe has the potential to shed new light on some of the deepest and most perplexing mysteries of modern astrophysics. The phenomenon of fast radio bursts, for example, is a major puzzle. These are incredibly bright and incredibly short, bursts of radio waves that seem to be coming from distant galaxies. Some of these bursts repeat with a strange and often eerie periodicity. The source of these bursts is completely unknown, and they release an immense amount of energy in a fraction of a second. Could it be that these are not astrophysical explosions in the classical sense, but are a form of natural, large-scale quantum teleportation event? A momentary, coherent collapse of the wave function of a vast number of entangled particles. A glitch in the cosmic teleportation network. The existence of ultra-high-energy cosmic rays is another long-standing puzzle. These are single, subatomic particles that arrive at the Earth with an energy that is millions of times higher than anything we can produce in our most powerful particle accelerators. The problem is that these particles should not be able to travel across vast intergalactic distances without losing their energy through interactions with the cosmic microwave background radiation. And yet, we see them. Could it be that these particles are not traveling to us in the classical sense at all? Could they be teleporting from their distant sources, arriving at the Earth with their energy intact, having bypassed the long and energy-sapping journey through intergalactic space? These are, of course, highly speculative ideas, but they are a testament to the fact that the universe is full of phenomena that do not seem to fit our simple, classical, and local understanding of reality. And the idea of a universal teleportation network provides a new and potentially powerful framework for thinking about these mysteries. But the implications of a teleportation universe extend far beyond the realm of astrophysics. It has profound implications for the future of our own technological civilization. If the universe is a natural teleportation network, then the ultimate form of travel and communication may not be about building faster spacecraft or more powerful transmitters. It may be about learning to hack the code of the cosmos, to tap into the underlying quantum informational network that connects all of reality. A sufficiently advanced civilization might not need to travel through space at all. They might be able to simply relocate themselves, to teleport their matter, their energy, and perhaps even their consciousness from one point in the universe to another by manipulating the deep entanglement structure of space-time itself. This could be the ultimate explanation for the Fermi paradox, the puzzle of why we have not yet seen any evidence of other advanced extraterrestrial civilizations. Perhaps they are not traveling between the stars in physical spaceships. Perhaps they have graduated to a higher, more efficient, and more subtle form of existence. A form that is based on the direct manipulation of the quantum informational fabric of the cosmos. They are not out there to be seen. They are everywhere, woven into the very structure of reality itself. This vision of a teleportation universe is a vision that is both breathtakingly beautiful and deeply humbling. It is a vision of a cosmos that is far more interconnected, more intelligent, and more mysterious than we can yet fully comprehend. And it is a vision that places information and its strange, non-local quantum properties at the very heart of reality. The universe is not a dead, mechanical thing. It is a living, breathing, and constantly communicating quantum web. And we, as conscious, questioning beings, are not just passive observers of this web. We are an integral part of it. Our own consciousness, with its strange and often non-local properties of intuition, of empathy, of creativity, may be a macroscopic manifestation of the same deep, quantum connectivity that allows for the spooky action of entanglement and the magical process of teleportation. We are not just in the network, we are the network. The quest to understand quantum teleportation is not just a quest to build a new kind of technology. It is a quest to understand the very nature of our own reality. And it is a quest that is leading us to a new and profoundly different picture of the cosmos, a picture where space is an illusion, where time is a mystery, and where the universe itself is a single, vast and beautifully interconnected quantum thought. For decades, the strange and beautiful phenomenon of quantum teleportation was a curiosity confined to the esoteric world of theoretical physics and the carefully controlled environment of the laboratory. It was a stunning demonstration of the bizarre, non-local nature of the quantum world. But its practical applications seem to be a distant, and perhaps even unattainable, dream. But that is no longer the case. We are now living at the dawn of a new, quantum technological revolution. A revolution that is poised to take the strange magic of teleportation out of the lab and into the real world. A revolution that has the potential to reshape our society, our economy, and our very understanding of information itself. The most immediate and most transformative application of this new technology is in the field of quantum communication. In our current classical world, all our communication, from a simple phone call to a classified government document, is fundamentally insecure. It relies on the principles of classical cryptography, which are based on the computational difficulty of solving certain mathematical problems. But these codes can, in principle, always be broken by a sufficiently powerful computer. And with the advent of quantum computers, which have the potential to solve these problems exponentially faster than any classical machine, the entire foundation of our modern digital security is under threat. Quantum teleportation and the principles of quantum mechanics upon which it is based offer a new and fundamentally different kind of security. It is a security that is not based on computational difficulty, but on the very laws of physics themselves. The no-cloning theorem and the observer effect guarantee that any attempt to eavesdrop on a quantum communication channel will inevitably disturb the system and leave a detectable trace. This allows for the creation of unhackable communication systems, systems where the security is guaranteed by the fundamental nature of reality itself. The technology of quantum key distribution is the first practical application of these principles, and China, with its ambitious and highly successful Mickey's satellite program, has already demonstrated the feasibility of creating a global quantum-secure communication network. In 2017, Chinese scientists successfully teleported the quantum state of a photon from a ground station in Tibet to the Mixius satellite in orbit, a distance of over 1,400 kilometers. It was a stunning and world record-breaking achievement, a clear demonstration that quantum teleportation is no longer just a laboratory experiment, but is a viable technology for global, secure communication. The race to build a quantum internet is now on, with governments and tech giants around the world investing billions of dollars in the research and development of the necessary technologies. A mature quantum internet would not just be a more secure version of our current internet. It would be a new kind of network, a network that can transmit not just classical bits, but fragile, quantum qubits of information. This would allow for the connection of quantum computers around the world, creating a global, distributed quantum supercomputer. The impact of such a technology on science, on medicine, on finance, on artificial intelligence would be almost impossible to overstate. This brings us to the second great technological revolution that is being powered by the principles of quantum information, quantum computing. As we have seen, a quantum computer is not just a faster version of a classical computer. It is a fundamentally different kind of machine. A machine that operates on the strange and powerful logic of the quantum world. And quantum teleportation is a crucial and enabling technology for building a large-scale, fault-tolerant quantum computer. One of the greatest challenges in quantum computing is the problem of decoherence, the tendency of the fragile quantum states of the qubits to be destroyed by their interaction with the environment. To build a powerful quantum computer, you need to be able to connect a large number of qubits together. But the more qubits you have, the more susceptible the system is to decoherence. Quantum teleportation provides a potential solution to this problem. It allows for the transfer of quantum information between different parts of a quantum computer, or even between different quantum computers in a network, without the need for a direct physical connection. You can teleport a qubit from a noisy computational part of the processor to a quiet, protected quantum memory, preserving its fragile state. You can use teleportation to create the long-range, entangled connections that are necessary for the implementation of powerful quantum error correction codes. The algorithms that will be needed to protect a quantum computation from the destructive effects of decoherence. In this sense, quantum teleportation is not just a communication protocol. It is an essential architectural component of any future large-scale quantum computer. It is the quantum wire that will allow us to build machines of unprecedented computational power. The societal and economic implications of this are staggering. A mature quantum computer could revolutionize the process of drug discovery and material science by allowing us to simulate the behavior of molecules with perfect quantum accuracy. It could transform the field of finance by solving complex optimization problems that are currently intractable. And it could supercharge the development of artificial intelligence by providing a new and far more powerful computational substrate for machine learning algorithms. But with this great promise also comes great peril. A powerful quantum computer would also be able to break most of the classical cryptographic codes that protect our current global financial and communication systems, creating a new and potentially devastating security threat. The race to develop quantum-resistant classical cryptography and to build a truly secure quantum internet is one of the most urgent and most important technological challenges of our time. The technological revolution of quantum teleportation is not just about building better computers and more secure communication networks. It is a revolution that is forcing us to confront some of the deepest and most unsettling questions about the nature of our own human existence. The possibility, however remote, of one day being able to teleport the complete quantum state of a complex biological system, or even of a human being, is a prospect that is full of both breathtaking promise and profound existential dread. As we have seen, This is not the beaming of science fiction. It is a process of destruction and recreation. And it raises a host of deep, philosophical questions about the nature of identity, of consciousness, of the self. Is the person who emerges at the destination still you? Or are you just a perfect, but ultimately soulless copy? These are questions that may not have a simple, scientific answer. They are questions that touch on the very meaning of what it means to be human. But even if we never teleport a human being, the very fact that the laws of physics allow for the perfect, non-local transfer of information is a profound and deeply transformative revelation. It tells us that our classical, intuitive understanding of the world, a world of separate, localized objects, is a profound illusion. The true reality is a much more interconnected, more holistic, and more mysterious quantum web. And as we learn to harness the strange and beautiful power of quantum teleportation, we are not just building a new set of technologies. We are learning to see the world and ourselves in a new and more profound light. We are moving from a worldview that is based on separation to one that is based on connection. We are moving from a reality of things to a reality of information. And we are moving from being passive observers of the cosmos to becoming its active and conscious co-creators. The journey into the age of quantum teleportation is a journey that is full of both immense promise and profound ethical challenges. It is a journey that will require not just scientific and technological ingenuity, but also a new level of philosophical wisdom, of social foresight, of human maturity. And it is a journey that is just beginning. The strange, spooky, and beautiful magic of the quantum world is no longer confined to the laboratory. It is coming into our world, and it is a world that will never be the same again. The ultimate question that the phenomenon of quantum teleportation forces us to confront is not about technology, not about communication, not even about the nature of space and time. It is a question about the very nature of reality itself. If information can be transferred from one location to another, instantaneously and without traversing the intervening space, then what does this tell us about the fundamental structure of the universe we inhabit? It suggests a reality that is far stranger, more interconnected, and more profoundly mysterious than our classical. Common sense intuition would ever lead us to believe. For centuries, our scientific worldview has been built on the foundation of locality, the idea that an object can only be influenced by its immediate surroundings. But quantum entanglement, the engine behind teleportation, shatters this foundation. It reveals a universe that is fundamentally non-local, a universe where the concept of distance itself may be an illusion. The two entangled particles, separated by light years, are not two separate things. They are two aspects of a single, indivisible, quantum whole. To touch one is to touch the other. This is a vision of the cosmos that is not a collection of objects in space, but is a single, vast, and interconnected quantum system. A system where space is not a fundamental, pre-existing container, but is an emergent property of the underlying quantum informational relationships between its constituent parts. This is the essence of the holographic principle. The idea that our three-dimensional reality is a projection of information encoded on a lower dimensional surface. In this view, quantum teleportation is not a process of information traveling at all. It is a direct manipulation of this underlying holographic code, a rearrangement of the informational bits and qubits that constitute the very fabric of reality itself. This is a profound and deeply transformative shift in our understanding of the cosmos. It suggests that the true fundamental reality is not the world of matter, of energy, of space and time that we perceive with our senses. The true reality is a world of pure quantum information, a world of abstract, mathematical relationships, a world of non-local, entangled connections, and the physical universe we experience is just a shadow, a projection, a fleeting and partial manifestation of this deeper and more fundamental informational reality. This informational view of the universe has the potential to unify some of the deepest and most disparate concepts in modern physics. The mysteries of dark matter and dark energy, the puzzle of quantum gravity, the nature of time's arrow. All of these may find their ultimate explanation in a deeper and more complete understanding of the quantum informational structure of the cosmos. The universe, in this vision, is not just a physical system, it is a computational one. And we, as conscious, questioning beings, are not just passive observers of this cosmic computation. We are an integral part of it. Our own consciousness, with its strange and often non-local properties of intuition, of empathy, of creativity, may be a macroscopic manifestation of the same deep quantum connectivity that allows for the spooky action of entanglement and the magical process of teleportation. We are not just in the universe is in us. And the quest to understand the one is inseparable from the quest to understand the other. The journey into the strange and beautiful world of quantum teleportation is a journey that has taken us from the laboratory bench to the very edge of reality itself. It is a journey that has challenged our most deeply held beliefs about space, about time, about identity, about existence. And it is a journey that has left us with more questions than answers. Is our universe just one of a vast and perhaps infinite number of other parallel realities? Is the flow of time an illusion? Is consciousness a fundamental and creative aspect of the cosmos? These are questions that may not have a simple or a final answer, but they are the questions that drive us forward. The questions that fuel our relentless and beautiful human quest for knowledge and for meaning. Quantum teleportation is more than just a scientific breakthrough. It is a philosophical revelation. It is a mirror that reflects back to us the deep, strange, and wonderful mystery of our own quantum existence. And it is an invitation, a call to adventure, a challenge to see the world and ourselves, not as a collection of separate, solid, and certain things, but as a single, vast, and beautifully interconnected quantum song. A song whose notes are still being written. A song whose final and ultimate meaning we are all, together, creating.